we're going to kick things off with Eden. She is, one of the emerging experts, I think, in how you can use federated methods in the context of building foundation models for detecting diseases. There's not many people on the planet who have really hands-on experience and like live and breathe the stuff every day. So we're like really, it's great to have her here to tell us about what she's been working on, where she thinks things are going, and then we can see again in a few months' time. We can check in with her in person at the Flower AI Summit. So, Eden, thank you so much for coming today. We're really interested to see what you're going to tell us. Yeah, thanks for sharing your thoughts and time.
Thanks very much, Nick. Let me share my screen and we can kick things off. So yeah, thank you very much again, Nick, for inviting me to come and speak to talk some a bit about my work that I've been working in the space of federated learning now for just over a year. I should probably start off by kind of explaining a little bit how I'm going to talk about some of my research today. So I'll give you a brief introduction about myself, as well as my research and my research group at UCL. And then I'll talk a little bit about some of the research that we've been doing in the space of federated learning, specifically in the healthcare sector with disease detection, as Nick mentioned. I'll go through some of the results that we've seen, as well as sort of the future directions that we're looking to work towards. So a bit about me. So I'm now officially a first year PhD student. I finished my master's in September. So I started my PhD at UCL as of September, so 3 months ago. And specifically working in AI for enabled healthcare systems. And my research specifically focuses on the development and evaluation of vision foundation models. So if you're not familiar with foundation models, think of your ChatGPTs, but specifically with image data. And I'm also an honorary research fellow at Moorfields Eye Hospital. So I access all of the retinal imaging data that we have here at Moorfields and use that primarily to drive all of the innovative work that we have here. In addition to these two roles, I also am a data research and AI scientist for Insight, which is the health data research program at Moorfields, which is an NHS-led initiative which makes use of the routinely collected eye data that we have at hospitals, both at Moorfields and University Hospitals, Birmingham, as well, to make that available to researchers outside of these NHS trusts to, again, drive more research forward. So the group that I'm part of at UCL is the Keen AI group, and we have kind of four main themes. And you'll see why I'll explain these, because my research kind of sits in a kind of Venn diagram of many of these different themes all together. So one of them specifically is the investigation of retinal diseases. So we have had multiple papers published in Nature Medicine around our research, specifically looking at disease detection using imaging data that we have at Moorfields, looking at diseases such as age-related macular degeneration, diabetic retinopathy, cataracts, glaucoma, using these imaging models primarily to detect disease early so that we can help treat patients earlier, as well as understanding how prognosis happens with disease. So how is a disease going to progress in a particular patient? We also are looking very strongly into how we can clinically validate these AI models that we develop. So it's great having them work in a lab, but how do we ensure that these things actually work in the real world? So some of the things that we've been looking at as a group are how can we use these AI models to, one, identify patients in clinical trials better, but also when we have an AI model, when we deploy it in a hospital, how is that taken on board by the clinicians? How can we improve the workflow? And how can we actually ensure that these systems work consistently once we've trained it and we actually put it out there in the real world? Another area of our research group is the study of oculomics, which is a term coined by our group a few years ago. And this is specifically looking to detect diseases that are outside of the sphere of kind of ophthalmology, but still using retinal images. So is it possible to take a retinal scan? So like, for example, you go to have your eye test, but detect whether or not someone will go on to have some sort of systemic disease, like will they have a heart attack? Will they develop some sort of neurodegenerative disease like Parkinson's? And a lot of our research is to understand whether there are associations between these systemic diseases and retinal imaging. And if there are, then can we build models that can actually predict these things? And then finally, one of our research themes within the group is that of foundation models. So as I mentioned, this is very much my kind of main area of research. Back in 2013, we actually published a paper in Nature that was the world's first ophthalmic medical foundation model trained on medical images here from Moorfields. So a lot of my work is primarily looking to expand upon this area of research. So can we build bigger and better models using these retinal images, but also how can we take this existing model and train it in different ways? Um, as we're all probably all very aware, federated learning is also one of my research themes, and I'm trying to link this in specifically with foundation models. And particularly, my research focuses on cross-silo federated learning as opposed to cross-device. I'm looking to use federated learning across multiple different hospital institutions, where each institution has quite a rich data set for many different patients across these hospitals, as opposed to cross-device, where you have lots of individuals joining in a big FL setup together. And in addition, there are two different types of kind of federated learning, or two main themes, the vertical versus horizontal. And my primary area of research is in horizontal federated learning, where you have a pool of clients who have data that is from the same feature space, but different samples of individuals. So the information that we're gathering on our individuals that we're using to train these models, we have the same sort of imaging across all of these patients. And what we're trying to do is essentially just use that data to train a single model. So why federated learning, and why is that particularly interesting in the sphere of healthcare and healthcare foundation models specifically? And I feel like it's actually come at a very perfect time in the federated learning world, as well as the kind of medical foundation model. And Nick, actually, at your talk at Europe's recently, you kind of briefly touched on this as well. That we're getting to the point now where people are trying to find ways of utilizing approaches to compute as well as data that will allow us to kind of take much larger steps in terms of these model developments. And healthcare, because of the barriers that we see in data sharing and around governance, we are very constrained when it comes to developing these sorts of models in a single institution in a hospital like Moorfields. We have a huge data set, but being able to collaborate with other institutions would significantly improve the quality and the generalizability of these models. In addition, federated learning, because of its nature, helps obviously reduce computational burden. So if we can spread that across hospitals unfortunately don't have the shiniest, fanciest GPUs. So that's also a huge benefit to us. And then finally, federated learning and fine-tuning of foundation models specifically sit in quite nice harmony, as federated learning, although it's a really great approach, there are still some challenges that come with this method of model training, in that obviously you're sort of kind of bringing things together, and it can take a while with multiple rounds to train a model that is comparable to a centralized model. However, the benefit of fine-tuning a foundation model is that a lot of the model is already learned quite a lot, so you don't need as many rounds to get to a point where the model is sufficient at actually performing the particular task that you want it to do. So they sit quite in good harmony. So the area of the kind of main subject that I'll talk about today is some of the work that I primarily worked on last year as part of my master's thesis. And this was to take the RET-found model, the model I mentioned earlier, which is the ophthalmic foundation model, to see if we could take that existing model, which is open source, and use an open source platform like Flower and fine tune it, but in a federated way. And we wanted to do that using exactly the same data that we used in the original experiments for the RET-found paper. So that is specifically to fine tune, adapt the foundation model to three primary tasks. The first was the 1 year prediction of fellow eye conversion to wet AMD. So whether a patient who already has AMD in one eye, whether within the next year will also progress to their other eye. And then two systemic disease tasks, which is whether a patient who had a retinal scan within the next 3 years will have a heart attack, or in the next 3 years will they progress to have Parkinson's disease. And these are things that the RET-found model is already a state-of-the-art model at achieving in a centralized way. But what we really wanted to explore within a federated setting was whether or not we can achieve these same results using something like Flower, which would hopefully in future enable us to then expand our data sets used to fine-tune these models with the kind of collaboration of other institutions, so that we could then actually improve on these results without having to change anything about the model itself. So as I mentioned, we primarily use the RetFound model, which at its base uses self-supervised learning for the pre-training aspect, and then uses supervised fine-tuning to develop the fine-tuned versions of those models. The pre-training was trained with 1.6 million images from Moorfields, in addition to using the ImageNet 1K dataset. And then for the fine-tuning, we used our ALZI dataset, which was one of the datasets I highlighted earlier, which is a combination of imaging data from Moorfields Eye Hospital paired with hospital episode statistics from hospitals all around the UK when a patient has been admitted into primary care. And what we were able to do with that data set is understand a patient who has come to Moorfields, if they have had an image taken of their eye, whether or not in the next 10 years they then went on to develop some sort of systemic disease, which is where we've been able to get that labeled data in order to do this fine tuning. At the base of the RetFound model, it is a masked autoencoder, and exploring the pre-training aspect in a federated way is something that we're very keen to do going forward, and it's something we're actively working on right now. But this work primarily is focused on the fine-tuning aspect, which is just a simple supervised task. So as I mentioned, we're using the ALZI dataset, which has around, for the different diseases, we have differing numbers of patients. So for the ocular diseases, we have around 6,500 AMD patients, of which with those who had actual retinal imaging, there are around 800. And then for systemic diseases, we had around 1,400 for the myocardial infarction, heart attack, and around 300 for patients who had Parkinson's. So varying numbers of data set sizes as well was also interesting to explore in a federated setting. And what was quite interesting was that we also were able to use the UK Biobank for our external validation, similar to the original RetFound paper, to ensure that once we trained a model, how well did that model generalize to an unseen data set? Due to the nature of UK Biobank, we only had data for the systemic diseases, so for myocardial infarction and for Parkinson's. They don't have data, unfortunately, for the conversion of wet AMD. And these data sets are still quite small, so we are looking to validate this work again on larger data sets that we have access to privately. So what did these experiments primarily involve? So as mentioned, we were using the RetFound model. We were fine-tuning that, which is taking just the encoder aspect and training that end to end. And we used Flower to simulate these experiments. But what was so great about the ALZI data set was that although it's collected from Moorfields primarily, Moorfields itself is made up of around 7 different sites around London. So we were able to distinctly separate the images into where they actually originated from in London and treat those as individual silos themselves. Obviously, within those, we have Moorfields Eye Hospital, which is the largest. So as a client, it contributed much more data than some of the smaller sites. But in this way, we were able to separate the data in a very natural way, based on different patient demographics that they were serving in these communities. So although we're simulating it, we are using real data that is truly in like a federated way. And we trained the model in a way that was very similarly trained to the original RetFound model in the original paper. So same number of epochs, just we integrated 5 rounds of aggregation using the most standard federated averaging approach, just as like a baseline to see how well it did before we started introducing any fun methodologies. And we compared the results using the same comparative net tricks used in the original paper. So as mentioned, in order to actually compare a centralized version of the RetFound model versus a federated version, we took 2 approaches to the data. So we did hospital-based partitioning, so where the data was split by the hospital of origin. So in some instances, the data was coming from all 7 different hospitals. Sometimes it was maybe only coming from 5. And then to compare against this, we also randomly partitioned the data. So the same data used to fine tune, but we split it equally and randomly across the same number of clients that were present for the same experiments, just to see if there was a significant difference within that training process. And what we found as a result of these experiments was that actually the federated approach did very well. There were very similar performances across most of the tasks. Where we saw that the federated model struggled more was the instances, for example, where with the Parkinson's data sets, where the number of images per client was already very low. So in splitting it and having these models trained locally, we found that the models struggled to converge more quickly than the centralized model. Um, However, I think this simply highlights the importance of understanding your data distribution and understanding what the quality within those clients themselves. So these are all things that, although are not unfortunate, we were definitely anticipating these results, and these are things that going forward we will try to overcome when it comes to making further experiments and building models that hopefully will improve on these existing technologies. So finally, what did we find from this? I think from what hopefully what I've conveyed, you can see that we do think it is a viable approach. So for the fine tuning of foundation models, we do think doing it in a federated way is achievable and viable. And we think that if you are able to ensure the quality of your data sets and have a good understanding of what difficulties federated learning can introduce into model training, and you're not just expecting it to work out of the box, then this is a very strong approach that actually can help you increase the data set sizes that you have, the diversity in the data sets, and hopefully produce models that are going to be stronger than their centralized counterparts. And in the future, that my work is primarily focused on going to be improving these experimental enhancements. So can we find ways to address these data quality and distribution imbalances? What happens if, for example, we change the number of server rounds and change the number of epochs on each local client? What sort of experiments can we come up with in that sense? And then the other thing we're very keen to explore is novel aggregation strategies. So in this particular research, we were only using the federated averaging aggregation approach, which is the most common and probably the most straightforward. However, we have seen a lot of research that has come out that is looking to utilize aggregation strategies that are specific for fine tuning. There's a lot in work in fine tuning for LLMs, for example, but not so much in the space of vision. But looking to use these methods could potentially help us in the context of federated learning to produce models that are trained more efficiently. And then finally, exploring the use of integrating federated learning into the full life cycle of the development of foundation models. So in the pre-training phase where you're doing self-supervised learning is something that I'm actively working on with a few institutions in the US at the moment. And then integrating that into the fine tuning aspect as well to have personalized models that you can have at each hospital site so that you have a model at the end that works equally well across all sites rather than having maybe a single centralized model that is the kind of compromise of all parties. So we have lots of excitement in terms of how we're envisioning federated learning integrating into our research going forward. And using Flower was super simple and straightforward in integrating into this particular research. I found that going from using Flower in simulation to then using it in a real setting with real collaborators, a very easy approach. And if you have any questions in regards to this research, as Nick mentioned, I will be at Flower Summit in 2025 in a few months' time, but feel free to reach out on LinkedIn or via my email. Thank you very much.
Awesome. Thank you for the talk. Very cool. So we have a few minutes for questions if people have any. So if you happen to be in the room, just raise your hand and I can unmute you. If you happen to be on Slack, you can ask the questions there. I'll have a brief look. Or if you happen to just want to, use the Q&A feature here, feel free. We can do this for 5 minutes if there's any questions. Um, I have one just to kick things off, and I was just wondering if you could just go back a few slides to the results. There was a little bit hard to see the
Oh yeah,
differences between the FL
absolutely.
and if in particular, I was just curious if you could just tell us like what the
Oh
differences were. Were they
yeah, let me share my screen again. Can you see the slides? Oh, there
uh
we go. Here we go. Yeah,
yeah,
so
so
we In regards to these three different on the right hand side, the very top row is the results we had for the first experiment, so for the ocular disease, so for wet AMD, and then underneath we have myocardial infarction and then Parkinson's. And the results on the left are for the area under the curve, and for the right it's the precision recall results. And what you can see is actually across the board they are very, very similar across all of these different experiments. On the far left, the first column is the centralized results. So that is the original RepFap model when I retrained it myself. And then on the right, we have three different experiments. We have when we trained using a single client using Flower. So we essentially just took exactly the same approach, and using it as almost like a litmus test to make sure that there was nothing significantly different between training the RepFap model from the original open source GitHub repo versus integrating it into Flower and seeing if there's any differences, and we found there was very little difference at all. The main differences between our experiments, between the RepMap one and the Flower based experiments, were the number of times the experiments were repeated. And an average, we didn't have the opportunity to do it as many times as in the original experiments. There are some differences in terms of the distributions, but with these are experiments that we're looking to repeat, and actually are already in progress. On the far right-hand side, we have the second from the left is the multi-client for, as I mentioned, for random setups and when we split it randomly. And then on the final column, we have the multi-client by hospital. And we actually found in general that the results when split by hospital actually did better than the randomized split, which actually makes sense, because the quality of the data that we were seeing across these institutions when split by hospital, there were some institutions that were contributing data that was in general quite poor. And actually, because of the way that the federated averaging algorithm works, the hospitals like Moorfields, who were contributing the largest and most significant amount of data, which was typically high quality, was kind of outweighing these smaller institutions that were still contributing information, but the data was maybe more inconsistent and had kind of more imbalanced labels as well. So it actually helped having the realistic setting versus just having everything be very jumbled and mixed together and be contributed equally in the final model.
I see. Interesting. Yeah, there's not many works out there that have really well justified partitioning of the data. So this is one that's really good with that.
And we're excited because the Alzey data set that I mentioned spans initially from 2008 to 2018. However, we're currently going through a process at the moment for renewal, and which will allow us to take the data back to 1997 all the way up to 2024. So we'll be able to expand this data set quite significantly, and it will still be partitioned across these different institutions that make up the Moorfields Trust. So in that way, we'll be able to continue these federated experiments with real data, but with much more higher numbers of images within those clients themselves. As at the moment, although this is still quite high compared to some experimentation, the more data, the better. We can have a better understanding of how these federated approaches work when we're working with kind of some of these clients had under 100 images, which in the grand scheme of things is not contributing a whole lot. So if we can introduce more, then it helps us understand how this will scale and how that contributes to the final model. And ultimately, if we can introduce more clients as well, then we can understand how that works in the development, these sorts of things.
Awesome. Very cool. Evelyn, I see you have a question. Feel free to unmute and ask your question.
Okay, yeah, Eden, thanks so much for this presentation and results sharing. Very cool to see the level of rigor in federated learning in practice nowadays. One of the things that I'm curious that how you approach the fine-tuning of these large models. As you pointed out, one of the huge benefits for FL is that people that want to participate don't have the resources of a big tech company with 10,000, 100,000 GPUs. So this whole field of fine-tuning with adapters, the LoRa style adapters that are much smaller, is interesting. Have you played with that? Does that work well?
It's something that we're actively experimenting with at the moment. So as I mentioned, I think initially we were quite keen to just see what a federated setting would look like, just with sort of very vanilla approaches. But yeah, absolutely looking at sort of more kind of parameter efficient approaches where we can, especially in real life settings where we're working with people sort of across seas, we need approaches that are actually going to be that will work in practice rather than just in simulation. So yeah, this is something we're actively working with, but these things all as with all of the things that are happening in the field of federated learning, it's all moving very quickly. So trying to decide where you sort of like draw a line in the sand and say, we're going to use this approach and just see what happens is kind of where we're at right now.
Okay, share what you find out. Very interesting.
Absolutely. Well, if you come in March at the flower talk, I'll be there for sure to share some new results.
Awesome.
We have another question that came in. The question is, if you had one wish, what feature would you want in Flower?
Oh,
If you could,
that's a
yeah.
good question. Um, I think I may have mentioned this in the past, but I
Mm.
really I think having better visualizations. So I work a lot with doctors, obviously working in a hospital, and trying to convey the how well a model is training is actually quite challenging if you're trying to explain to someone who is maybe not familiar with the evaluation metrics or what multiple server rounds means in the context of training a model. So having good better visualizations that I can share and use to explain how well a model is training through the federated learning process. Similar, maybe something like with like TensorBoard would be wonderful. And I know that that's something that there are ways to do that yourself at the moment, but having something integrated into the system so that people can more easily plug and play and have an overview of how well these things are going and looking at specific metrics, I think would probably be useful. But a lot of the things that I've wanted in the past have been ticked off my flower wish list, so I'm very happy.
Okay, great. I see. But I can see why the visualization thing would be, I guess, important. I suppose you're highlighting that if it's built in, it would just be
Mhm,
um, more powerful than having to like take some other tool and configure it
mhm.
and plug it in and so on. Because it's just so fundamental, I guess you're saying, because you can, okay.
Yeah, absolutely. And I think especially given that I work in a field that is working so closely with clinicians. A lot of clinicians are very interested in federated learning, but they don't have a lot of AI experience, and they definitely don't have a lot of federated learning experience. So ways that which we can sort of help bridge the gap in terms of the kind of technical and clinical conversation. All of these things, I think, aid in that, and having something that's built into the system, I think, gives clinicians more trust that what they're doing and what people are implementing actually they can see the results themselves.
Yeah, got it. Cool. Great. Well, thank you so much. We should move on, but this is amazing work. I can't wait to see where it goes. And thank you for doing it.
Thank you very much again for having me speak.